I do my hair toss, check my nails. Baby,
Welcome to our second half of the course, which will mostly be themed on vectors. It represents a very big shift from calculus, so we're going to kind of put all the calculus stuff on the shelf and now focus on a concept called the vector. For those of you that are studying business and commerce, my condolences. A lot of this stuff really has mostly physics applications. So vectors in and of itself have more applications in the world of engineering and science than they do business and commerce. The calculus stuff for sure has applications in economics, but not so much the vectors. So anyway, before we get going, let's spend most of this lesson talking about what a vector is and some of the terminology that's surrounding it, and just perfecting that or making sure we understand or we're having that common language to talk about. So a vector is a quantity that basically has a magnitude and a direction. So it has a size, so there's a quantity associated with it, a number, and a direction, which also has something to do with numbers, degrees for direction, north, east, southwest, all that stuff. And we draw a picture of these things by using a line segment. So to take that abstract notion of something that has magnitude and direction, like pushing something, we draw a picture of a push, and that picture of the push has two elements to it. It has a direction. You can see my line segment here has an arrow at the end of it here, and it has a magnitude. It has a length. So the length of that line segment basically denotes how strong the push was, and the direction of that arrow, the direction of that push. Here at the bottom, just again, a little bit of terminology. Okay, so we've got a vector. So vector AB, you can see there's this little line with an arrow up above it. So that denotes the vector AB, so from A to B. We can also just use one single lowercase letter to denote the vector. So in this case, we called that vector vector V. So we can call it vector AB or we can call it vector V. Furthermore, the magnitude of that vector, vector AB, can be denoted by this symbol. It looks like the absolute value symbol. So basically the magnitude of vector AB. We could also obviously have said the magnitude of vector V. That would have been perfectly appropriate there too. Okay, so here are a couple of examples of things that require vectors. Now you can sort of recall what I said in the intro there. All three of those are very physics-heavy concepts, right? Displacement, velocity, forces. All of those things are things that you would see in a physics class if you haven't already. And so these are all considered vectors because they have direction and they have a magnitude associated with them, right? So this student walking home from school 3 kilometers due east, right? That 3 kilometers is its magnitude, that direction east. Similar here with velocity, right? So velocity gives us a magnitude. That magnitude is a speed, and it's given a direction, north 20 degrees east. So that's the distinction between speed and velocity, right? Speed is a magnitude. Vector would be our velocity, because velocity has speed and direction attached to it. Forces, so basically, again, this is similar to that example of when I was talking about pushing something, or in this case, the force of gravity. The force of gravity on 1 kilogram mass is 9.8 newtons downwards, right? So again, force of gravity pushing downwards towards the earth, and it's giving us that direction and that magnitude. Okay, so not to be confused or conflated here, these four examples are what we call scalars. They are not vectors. So they have a number associated with them, but they don't necessarily have a direction associated, right? So age, length, area, speed. I think I mentioned speed a second ago. Speed doesn't have a direction associated with it. We would just say, oh, he was traveling at a speed of 20 kilometers per hour. Well, in what direction? If we gave a direction along with that speed, it becomes a vector and therefore a velocity. Here's a very, very quick example. I'm not going to insult your intelligence by asking you to pause the video and do any work here, but I just want you to take a look at this. Have a very, very quick thing. The magnitude of this vector. So car is traveling 80 kilometers per hour in a northeast direction. That's a vector. We could represent this as a vector AB. So I've drawn a little quick diagram here, vector AB. The magnitude of this vector is the same as the speed. So essentially the magnitude, again, there's that symbol there for magnitude. The magnitude of that vector is hopefully obviously 80, right? Its magnitude is 80 because the velocity of that car is 80 kilometers per hour northeast. There's your scalar, there's your direction, right? So we have a number and a direction. So in this example, this is important for a couple of other things we're going to talk about. The starting point for this car was kind of irrelevant when we're talking about the velocity, right? If the car traveled 80 kilometers per hour in a northeast direction, its vector, whether it started here or whether it started here, is kind of irrelevant because when we're talking about the vector, we're talking about the forces on that object, right? So the car traveling 80 kilometers per hour in a northeast direction is the same if it starts here or if it starts there. And this slide kind of talks about that. So if a vector is translated, it's still basically the same vector. In other words, if I push a box with a certain force in a certain direction, it doesn't matter whether I push that box in with a certain force in a certain direction here in my house or out on my street or back at the school or anywhere else, right? So that's a very sciencey notion as well, right? So in terms of an experiment, right? Like if I do something here, it should work here. It should work somewhere else as well, if all things are considered equal, right? So, and that's essentially the crux of what we're using vectors for. Okay, so if a vector is translated, in other words, moved left, right, up, down, it's still the same vector because it still has the same magnitude and it still has the same direction. So, and this kind of is a bit of an obvious statement. Basically, vectors are equal if these conditions are met. So hopefully those are all pretty obvious, but I'll take them down one at a time. Vectors are going to be equal if and only if, just in case you weren't sure, that IFF stands for if and only if those two vectors have the same magnitudes. So in other words, those two line segments are the same length. And also, this has to be met, the direction from A to B is the same as the direction from E to F. So this direction from A to B has to be the same between E and F, right? They are pointed in the same direction. And number 3 kind of is just a bit of a tag along, right? If they are pointed in the same direction, those two line segments must be parallel to each other. Okay. Now, of course, we can't get away with not stating number 2, right? Because if I just stated number 3, that arrow needs to be addressed as well. Okay, right? So if AB is pointing in this direction and if EF were pointing in this direction, they would not be equal vectors. In fact, they would be opposite vectors, right? So I have an example here of opposite vectors. Those two vectors basically are not equal because they point in like perfectly opposite directions. So two vectors are going to be opposite if they have the exact same magnitude and the exact opposite direction. Because we can translate vectors left, right, up, down, we can push or pull the vectors together to create an angle. And that angle has importance and it has relevance, and we'll discuss that further on. But the angle between those two units basically is the angle when they are placed tail to tail. So if I translate the vectors and I place them in a diagram such as that. Vectors can also be multiplied by scalars. So in other words, we can stretch vectors. Okay, and that's a pretty basic notion. Like if you've done any of our functions and things like that, a values, multiplication stretches things, right? So it's no different here. If I took a vector A, if I took a vector A and I multiplied it by 3, you'll notice that this vector basically 1, 2, 3. It's 3 times the length of the original vector. You'll notice that I can also multiply them by negative numbers. So if I can multiply by negative numbers, that basically just switches its direction, kind of like a vertical reflection when we're talking about functions. So it's really very intuitive stuff. Okay, so if A is a vector and K is an element of all real numbers, then we can multiply a vector by a scalar. If we multiply a vector by a scalar, it gives us basically a vector's magnitude multiplied by that scalar, right? So that should hopefully kind of be obvious. The directions of basically those are going to be the same if K is positive and opposite if K is negative. Again, that's pretty intuitive. Multiply by a negative number, turn it in the other direction. The 0 vector, again, almost goes without saying, but yes, the 0 vector is a thing that exists. I guess we can't really draw it because it has a magnitude of 0. I can't draw something that has a magnitude of 0. But, theoretically, if I don't push a box, it has a 0 vector, right? So basically, that's a vector that has magnitude of 0 and indeterminate direction because I'm not pushing the box. A unit vector is essentially the boiled down version of a vector. It's kind of like the simplest form of a vector. So what we can do with a vector is boil it down so it has a magnitude of 1. And generally speaking, when you have any vector, if you divide it by its magnitude, you would have basically compressed it, right? So that goes back to that scalar multiple piece. If the scalar multiple itself is 1 over the magnitude, we're basically dividing the vector by its own magnitude. So this vector here would basically have a magnitude of 1. Notice that symbol right there. That symbol denotes that it's a unit vector. So it has a magnitude of 1. Of course, it has a direction, and that still makes it a vector, but it has a magnitude of 1. Okay, so what I want you to do is pause your video in a second to try and complete this one. This question is asking you to find basically all of the equal vectors in this diagram of the parallelogram. Now remember that direction matters, okay? So I'll give one away here. Vector dA is equal to vector CB, right? They are equal because they both have the same direction because it's a parallelogram and the same magnitude because it's a parallelogram. Okay, so that basically solidifies that those two are in the same direction. Now, the only catch is that, of course, you could not say vector dA and vector CB. Vector dA and vector CB are not in the same direction and are therefore not equal vectors. They're opposite vectors, okay? So take a second or two, pause the video, write down a couple of those, and I'll give you a couple of answers because there are a lot of answers here to this one. All right, so thanks for pausing and pondering that one. I'll give you a couple of examples. We talked about dA and CB a second ago, but AE, the key question here was, would AE be equal to anything? And just a fun fact about parallelograms is that, AE is equidistant to EC. So those two vectors, AE and EC, would be equal. DC would be equal to AB. That's a pretty common one that a lot of people throw out there. DB, really good question here, is would DB be equal to AC? And the answer would be no, because they don't have the same direction. They have the same magnitude, but not the same direction. Right? So there are a lot of answers possible here for that one. So I'll just kind of leave that up to you. Example 3 here. So what I want you to do is pause the video and consider these examples here. Which of the following are scalar quantities and which ones are vector quantities? So take a second or two, pause the video and give those a go. All right, so there's your answer for all of those. I underlined kind of the key words there that would give us away that we were talking about vectors. So for the first one and the last two, the first one we're talking about from the north. The second last one we're talking about traveling northeast. And in the last one we're talking about a bearing of 188 degrees. So all three of those have some form of direction matched with their quantities, right? And so that's what makes them vectors. These two here are scalars because, again, that 70% is not telling us a direction, right? If I said an increase of 2%, that could be considered a vector, right? If I said a decrease of 0.5%, that could be considered a vector. But here we're just talking about their mark, one mark, 70% achieved. Okay, so that's just a scalar. Same thing in terms of the temperature, right? A temperature of 23 degrees. Again, I guess you could talk about an increase in temperature as being a vector or a decrease in temperature being a vector. But in this case, we're just making a statement, temperature of 23 degrees. There's no direction attached to that. So I hope you basically got some just basics out of what a vector is and a couple of principles behind what we're going to be doing with vectors. Try a couple of the examples that are posted on the website and just get your feet wet with some of the terminology and some of the aspects of vectors and some of the language we're going to be using throughout the unit. And that's it for today. Have a good one.